Visibility is used to quantitatively express how clearly an object is seen by the human eye. The main factors that affect visibility are brightness, size and distance of viewing objects, background brightness contrast, recognition time and glare. As the brightness increases, the visibility increases. Excessive brightness can easily cause eye fatigue and should not exceed 16 silb. This graph reflects the relationship between illuminance and satisfaction. From this, it can be seen that hair satisfaction is concentrated between 1,500 and 3,000 lux. If the illumination is too high, the number of satisfied people will decrease, indicating that the illumination should be moderate. The viewing angle is formed by the size of the object and the distance of the eye from the object. This is the size to be identified. Large and close objects have a large viewing angle and high visibility. Luminance contrast refers to the difference in brightness between the viewing object and the background. The greater the difference in brightness, the higher the visibility. For uniformly illuminated matter backgrounds and targets, light reflectance can be used instead of brightness. The visual efficacy curve reflects the influence of three factors: illuminance, viewing angle, and brightness contrast on visibility, as can be seen from the figure. 1. The viewing angle of the same curve remains unchanged. If the contrast decreases, the illumination needs to be increased to maintain the same visibility. That is, the lack of contrast is compensated by the increase in illumination, and vice versa. The contrast is increased to compensate for the lack of illumination. 2. Different curves have different viewing angles. The smaller the viewing angle, the greater the required illumination. 3. At the same viewing angle, natural light is more conducive to the improvement of visibility than artificial light. There is not much difference when the viewing angle is large. Recognition time follows the Bunsen rock law. That is, the product of brightness and time equals a constant. That is to say, if the recognition time is short, higher brightness is required. Therefore, in order to recognize the moving object, and the recognition time is short and the recognition is difficult, a higher illumination standard needs to be adopted. Adaptation refers to the process that when the light environment changes, the human eye suddenly changes from seeing clearly to seeing blurred, and then sees clearly again after a period of time. The short adaptation time from dark to light is called light adaptation. The longer adaptation time from light to dark is called dark adaptation. As can be seen from the figure, light adaptation takes 30 to 35 minutes, and dark adaptation only takes 5 minutes. It indicates that the transition space should be considered in place where the ambient brightness changes too much, in place where human eyes need to change the direction of their gaze. The difference in brightness between places of sight should not be too large. Glare is a visual phenomenon in the field of view that causes discomfort or reduces the ability to observe details of objects due to an unsuitable distribution or range of brightness, or excessive brightness contrast. According to the degree of glare's impact on vision, it can be divided into disability glare and discomfort glare. Disabling glare reduces brightness contrast, reduces visibility, and even lose vision, but does not naturally produce uncomfortable feeling. Uncomfortable glare creates uncomfortable sensations, affects concentration, and can cause visual fatigue if exposed for a long time, but does not naturally reduce visibility. Disabling glare can be eliminated by limiting discomfort glare. From the glare formation process, it can be divided into direct glare and reflected glare. Direct glare is produced by light source in the field of view, especially luminaries that exist close to the direction of sight. Reflected glare is caused by reflections in the field of view, especially when the reflected image is seen close to the line of sight. Reflected glare is more difficult to avoid. Methods to reduce direct glare include 1. Limit the brightness of the light source. Use translucent or opaque materials to block the light source and reduce the brightness of the light source. 2. Increase the background brightness of the glare source and reduce the brightness contrast. 3. Reduce the viewing area of the glare source. For example, if the lamp is made into the shape of the left picture, the solid angle formed by the glare source to the eyes is reduced. 4. Increase the elevation angle of the glare source as much as possible. As can be seen from the figure on the right, the glare is serious when the elevation angle is less than 27 degrees, and the glare is reduced when the elevation angle is greater than 45 degrees. However, the elevation angle is limited by the height of the floor, and the high installation position of the light source is not conducive to the lighting of the work surface. Therefore, sometimes it is necessary to use lamps to block the glare light source. Methods to reduce reflected glare include 1. Try to choose a metal surface for the visual work surface to avoid reflection glare caused by regular reflection. 2. Visual tasks avoid and stay away from regular reflection areas. 3. Use a light source with less luminous surface area and low brightness. 4. Reduce the proportion of the illuminance formed by the glare source, causing regular reflection in the total illuminance. Color is a visual perception attribute arbitrarily composed of chromatic components or achromatic components, which affects the quality of the light environment, affects people's physiological and psychological activities, and affects work efficiency. Color includes light source color and object color. Light source color is the color stimulus emitted by the light source. Object color is the color of an object that is perceived after light is reflected or transmitted by the object. Colors are divided into two categories, achromatic and chromatic. Achromatic refer to perceptual colors that have no hue. For object color, when the light reflectance of the surface of the object is greater than 0.8, it is white, and when it is less than 0.04, it is black. For the light source color, it is white when the brightness of the light is very high, gray when the brightness is very low, and black when there is no light. Color has three properties: hue, lightness, and chroma. Hue is a visual perception characteristic that distinguishes its color. The hue of the light source depends on the human visual perception produced by the spectral composition of the radiation. The hue of an object depends on the spectral composition of the light source and the visual perception produced by the proportion of light radiation of its wavelength reflected or transmitted by the object. Lightness is a visual perception characteristic of a color relative to light and dark. The higher the brightness of the light, the brighter the human eye feels, and the higher the lightness. The lightness of an object's color reflects the change in light reflectance or light transmittance. Objects with large light reflectance or light transmittance have high color lightness, and vice versa. Achromatic only has lightness, no hue and chroma. Chroma refers to the purity of color. Monochromatic light has the highest chroma, and the more white light components are added, the less saturated it is. The chroma of an object's color depends on the degree of selectivity of the object's reflected or transmitted spectral radiation. The higher the selectivity, the higher the chroma of the object's color. A system of equation color by series regulars and definitions is called a colorimetric system and is used for color quantification. There are two types of colorimetric systems. One is a system expressed by color stimuli, such as the CIE 1931 International Standard Colorimetric System. The other is a system expressed by the color alters of sensory indicators, such as the muscle colorimetric system. The muscle colorimetric system is the current international colorimetric system For object colors, the symbol H represents chromaticity, the symbol V represents lightness, the symbol C represents chroma, and H, V, and C are called muscle symbols. Color is calibrated with HV/C, and colorless is calibrated with HV/S. For the spectral color of a certain wavelength, the corresponding spectral stimulus values can be found in this figure, and the spectral color can be obtained by adding them according to the color mixing rule. The three spectral stimulus value curves in the figure represent relative spectral sensitivity, respectively representing the amount of red, green, and blue required for isonergetic spectral stimulation of its wavelength. The uppercase XYZ is the stimulus value of the color. X and Z only represent the chromaticity, and Y represents the chromaticity and light quantity. The light quantity include luminous flux, light transmittance, light reflectance, brightness, and brightness factor. The lowercase xyz are the chromaticity coordinates of the color. These are respectively equal to the ratio of the primary color, stimulus value of red, green, and blue, to the sum of the three stimulus values. These are respectively equivalent to the ratio of the primary colors of red, green, and blue, because x plus y plus z equals 1. Two chromatic coordinates, x and y, are generally used. Next, let's do an exercise. Given the relative spectral power distribution of the lamp, as shown in the table below, find the chromaticity coordinates of the light source color. According to the chromaticity coordinates of the light source color, take k equal to 1, phi lambda is equal to s lambda, take the lambda equal to 1 nanometer, and substitute the data into the chromaticity coordinate formula. Calculate that the x and y coordinates are 0.2498 and 0.3123 respectively. According to the calculation result, the color can be determined on the CIE 1931 chromaticity diagram. Although its point on the CIE 1931 chromaticity diagram represents a certain color, when the position of the chromaticity coordinates changes very little, the human eye will still think it is a rainbow color and cannot feel this change. The range in which the human eye does not perceive a color change is called the broad capacity of color. It can be seen from the figure that the wide capacity of color is different in different positions of the CIE 1931 chromaticity diagram. The blue part is smallest, and the green part is the largest. This means that the human eye can see a large number of various blues. This is relatively a small number of various greens. In the light environment design, the color quality of the lighting source has a great influence on the light environment, which can change the color of the illuminated object. The reason for the change is that the spectral power distribution of the light source changes, resulting in different spectral power distributions of the reflected light of the illuminated object. This in turn changes the stimulus values, resulting in changes in color perception. The adaptation of the visual system to the field of view also has an impact on color perception, known as color adaptation. For example, after the human eye has adapted to viewing objects in sunlight, when suddenly changed to indoor incandescent lamps, the indoor objects will look yellow. After a few minutes, the vision adapts to the color of incandescent lamps, and the color of indoor objects tend to be the same color in sunlight. Visual adaptation refers to the process of change in state of the visual system, including light adaptation, dark adaptation, and color adaptation, under the stimulation of various brightness, spectral distribution, and viewing angles presented now and in the past. The color quality of a light source is usually characterized by color temperature and color rendering, since the black body radiation at different temperatures corresponding to a certain light color. The color of the light source is represented by the different light color emitted when the black body is heated to different temperatures. The black body temperature when the chromaticity of a certain light source is exactly the same as that of a black body at a certain temperature is called the color temperature of the light source. The spectral power distribution of thermal radiation light source, such as incandescent lamps, is similar to the distribution of black body radiation, and the color temperature can be used to describe the light color properly. The spectral power distribution of gas discharged light source, such as a fluorescent lamp, is very different from the black body radiation, and its chromaticity coordinates can only fall near the black body locus. Therefore, the color of the light source can only be approximated by the light color of the black body radiation at a certain temperature. The black body temperature when the chromaticity of a certain light source is closest to the chromaticity of the black body at a certain temperature is called the correlated color temperature of the light source. The color rendering of the light source is used to evaluate the color change feeling of the object color under different lighting conditions, indicating the influence of the lighting source on the color table of the object. This perception is produced by the observer intensity or unintensity, comparing it with the color table on the standard light source, and represents the characteristics of the light source, showing the color of an object when compared with the reference standard light source. The color rendering of a light source mainly depends on spectral power distribution of the light source. The color rendering of continuous spectrum is better. The light source radiation, composed of several specific wavelengths of color light, also has a better color rendering effect. The color rendering of the light source is measured by the color rendering index, which is expressed by the general color rendering index and the spectral color rendering index. Under the illumination of the measured light source and the standard light source, when the color adaptation state is properly considered, the measure of the degree of conformity of the psychophysical color of an object is called the color rendering index. A measure of the degree of conformity with the psychophysical color of the CIE color symbol is called the spectral color rendering index. The average value of the CIE 1974 spectral color rendering index of the light source for a spectral group of 8 color symbols is called the general color rendering index. The minimum value of the color rendering index is set at 100. It is generally believed that the general color rendering index of the light source is excellent in the range of 100 to 80. The color rendering is average in the range of 79 to 50, and the color rendering is less than 50, because the general color rendering index is an average value. Even if the general color rendering index is the same, it cannot be determined that the color rendering properties of the two light sources are exactly the same. Think about it. The higher the color rendering index, the better. What occasions require high color rendering? In what occasions can a light source with defective color rendering be used?